Et aujourd'hui, avec vous, pour fêter les 70e anniversaire des Houches. En fait, moi, j'étais ici comme un étudiant et aussi comme prof plusieurs fois. Et chaque fois, c'était vraiment un plaisir. Et l'école des Houches a vraiment joué un rôle très important dans ma communauté, ça veut dire physique statistique. Et donc, on est très content d'être ici. Et donc aujourd'hui, en fait, je pense que je serai le premier orateur à faire mon exposé en anglais, parce que je suis, tout simplement parce que je suis plus à l'aise en anglais scientifique. Je suis désolé, j'espère que vous allez m'excuser. Donc, okay, so I switch to English now. So I'm going to talk about stochastic resetting. So it's a subject on which I've been working for the last 10 years with various collaborators, whom I'll acknowledge at the end. And as we'll see that, the basic idea behind stochastic resetting is extremely simple, almost trivial, but yet it has found many applications from search processes to computer science, queuing theory, and chemistry, and many other fields. And last 10 years have seen a lot of development, both theoretical and experimentally. And so what I'll do today is to just tell you our original motivation behind this problem and what are the main questions. And at the end, if I have still time, I'll talk about some recent experiments which are done in collaboration with the group of Sergio Ciliberto at ENS Lyon. And it's a beautiful experiment. So let me start by what is stochastic resetting. I mean, all of us are familiar with search problems. They are very common. So for example, animals searching for food, or a helicopter searching for survivors after a shipwreck, or a protein searching for a target site on a DNA to bind, or even when you are writing computer programs, when you are debugging, when you are looking for a bug in your computer program. And in all these, many of these problems, so I mean, natural intuition tells us that, okay, if you have searched for something for a while, I mean, probably you should not continue. You should take a pause, go for a coffee, and come back and restart the search. I mean, we do that. I mean, for example, if you are searching for a bug in your computer, I mean, you might get bogged down in a subroutine. After a while, you don't know what to do. So then you go for a coffee, come back, and restart. And chances are that this time you will find the bug. Okay. So this is sort of intuitive, and it has been there for a long time. And let me give you one more example, which is about visual search. So imagine that you are looking for, the face of a friend in a big crowd like this, and you ask, how do we actually search? How do our eyes search? Okay, it never does, scan from one end to another end. It sort of starts at a random point. It does a local diffusion. It comes back to the starting point, and then it restarts again. Okay. In fact, psychologists do this experiment. So they show a patient a blackboard full of the letter P, and there is one single B in this P, and you're supposed to find this B. Okay, yeah, some people have found it already. So, and then what they do is they put a camera in the eye, and they just look at the trajectory, how the eye is moving. Okay, and what you find is typically that you start from, let's say, this point, and your eye sort of does this kind of diffusion, and then it comes back. And this is resetting. It comes back to the starting point, and then it starts a new trajectory. So this is quite common. And now let me give one more example, which is from the combinatorial optimization problems. Imagine that you are looking for the ground state in a very high dimensional landscape, and so you start from some other configuration, and you do typical technique like simulated annealing, and then you are moving in this landscape, and quite often what happens is that you will get stuck in a metastable configuration, and then you don't move at all. And so what you do, so it was known empirical observation that it's better to go back to the initial point and restart. And the rationale is that if you restart, that you might find a new pathway, you can avoid metastable state, and maybe you will find the global minimum, which is your target at some point. Okay, so these ideas were there empirically for a long time. But there was no quantitative estimate. Does resetting really help you improve the search time? So about 10 years back, with my colleague Martin Evans from University of Edinburgh, we decided to sort of study this in a very simple model, just to have a quantitative idea. I mean, does resetting really help? So the model is very simple. I mean, I just want to show you this model in a one-dimensional setting, but you can easily generalize to higher dimensions. So the model is following. So imagine that you have just one dimension and you have a particle which starts at initial point x0 and it just does diffusion, and the only new ingredient is the following. So the dynamics takes place in continuous time. So if you are doing simulations, what you do is that in a small time delta t with probability r delta t, so r is the rate of resetting, with probability r delta t, you go back to your starting point, and with the complementary probability 1 minus r delta t, you just do diffusion. That means you just increment your position by a random noise, okay, which is the Gaussian white noise. So that's it. R is the only parameter in the model. So what this means, if you look at a trajectory, is that it undergoes free diffusion for a random interval of time, which is Poissonian distributed, exponentially distributed with parameter r. So when r is 0, it's just a plain diffusion. So now you introduce this r, and this is the model, resetting model. So before even asking for the time to search a target, you can ask, what happens? I mean, if I just put this small r, just introduce this resetting rate, what happens to the position distribution of the particle? Okay, that's the first thing to ask. And so we all know that, when r is 0, just plain diffusion, you have this usual Gaussian propagator. And now you just introduce this r, and you ask, what's the probability distribution? Okay, and this was already something interesting, because you can easily write down the Fokker-Planck equation for this. So there's a usual diffusion term, and due to resetting, if you are at position x with rate r, you are going away from x. So there's a loss term here, and there will be a gain term. If you are at x equal to x naught, you gain by resetting from other positions, and you have to solve this Fokker-Planck equation with this initial condition. Okay, it's trivial to solve, and but the solution you can actually express at any time t in a sort of suggestive form, which is like this, which has actually a very nice renewal interpretation. So what you do here, you look at any particular trajectory. Now there are two possibilities. Either you have no resetting at all. If you have no resetting, then the probability that there is no resetting in this time interval 0 to t is e to the power minus rt, and then you are just doing free propagation. So there's a p0 of xt. So this is just a Gaussian free propagator. And then other possibility is that you have more than one resetting. So in that case, you can use a kind of a renewal structure. So the trick is to look at the time when the last resetting happened. So this is your measurement time. You look backwards and find out the time when the last resetting happened. Suppose this is tau. Because the reason you are finding the last resetting time, because after that it's free propagation. There is no reset after that. Okay. So this is this term here. This is the free propagation during this last interval time, and you can ask what's the probability that the last resetting happened between time t and t plus d tau, and this is just this exponential distribution, and then of course you have to integrate over the last resetting time from 0 to t. So you can check that this is an exact solution of this equation. But the reason I wrote it this way, because you can immediately generalize this to any higher dimensions or for any stochastic process. Okay. So basically this says that you can write down the probability distribution in the presence of resetting in terms of the probability distribution in the absence of resetting. Okay. So this is a very simple form, and then in particular you notice that when t goes to infinity, this term drops out, and you just have this integral which you can perform exactly, and it's just exponential minus x naught with alpha naught equal to square root of 4, square root of r by d resetting rate. Okay. So you reach a stationary state. So basically you are resetting continuously. So dynamically you are generating a potential which drives the system into the stationary state. And the point is that this stationary state is a completely non-equilibrium stationary state. Why? Because the resetting move, it violates the detail balance manifestly, because you are always going back to the origin starting point. And so the stationary state actually has a non-zero current in the configuration space. Okay, and so even though the stationary state you can write down as exponential of some effective potential, this effective potential is only generated dynamically. It's not equilibrium potential basically. Okay, and so this was our prediction long time back. And just to show you here that recently from the group of E.L. Roekman in Tel Aviv University. So they measured using holographic optical tweezers this stationary distribution, and it matches very well with the theoretical prediction. I'll come back to the experiment a little bit later. Okay, so this is the first observation, and the second observation is that you have the full exact solution at any time t, and you can ask how does it relax to this non-equilibrium stationary state. Okay. And what we found is that there is a very unusual temporal relaxation. I mean, you have the exact solution, you just have to analyze this integral in time. And what you find is that this is a space-time picture, okay, space and time. And what you find is that for a given fixed time t, there is a length scale here, psi of t, which increases linearly with t with a constant velocity, which is square root of 4 dr. So it's like a light cone moving away on both sides. And inside the light cone, in the purple region, if you look at the probability distribution of the position, it becomes time independent. Whereas outside the light cone, it still depends on time. So in some sense, this light cone separates the between two types of trajectories. These are typical trajectories which have undergone lots of resets, and these are rare trajectories outside which have not undergone that many resets. Okay, and so this is a bit unusual, relaxation. So which means that this non-equilibrium stationary state, it gets established on larger and larger length scale as time progresses. And you can actually write down this in a more standard large deviation form. So this is exponential minus t into some rate function, which is a function of x minus x naught over t. And so what you find is that this rate function, as you go like this, at the light cone, it has a discontinuity. In fact, the second derivative is discontinuous, which indicates that there is a kind of dynamical phase transition, at time t, between the typical trajectories and atypical trajectories. Okay? So this was very unusual sort of phenomenon in this relaxation process. Okay, now let me come to the main question that I started out with, and that does resetting really help to find a target? Okay, so this was intuition, but does it really help? So we decided to compute this in this simple model, and so before we put the resetting, let us just remind you that what happens just with a simple diffusion. So if I have a one-dimensional problem, for example, and if I start at x naught, and suppose now I have a target sitting at the origin, and you ask, when does this searcher find the target for the first time? That is your search time. Okay? But to solve this problem, this is a classic problem, so you can easily solve it. To solve it, what you should look at is the survival probability. That's the easiest way to look at it. So survival probability means starting at x naught, what is the probability that the target survives? That means searcher does not find the target up to time t. And it's very easy to write down a sort of backward Fokker-Planck equation, backward in the sense that you are treating the initial position x naught as a variable. And this satisfies just the diffusion equation, and you have to put an absorbing boundary condition, because if you start exactly at x naught equal to 0, you will immediately find the target, so the survival probability is 0. So the solution is well known. I mean, it's just in terms of error function. Error function is just integral of Gaussian. And from this, once you have the survival probability, you can calculate the first passage probability, which is just the negative time derivative of survival probability, because survival probability means that the first passage occurs after time t, so you just have to take a derivative. And what you find is this classic, the 1D Brownian motion first passage probability distribution, and you find that it has as a function of t, it has a fat tail, it decays like t to the power minus 3 by 2, which means that even though the distribution exists, its first moment is divergent. Okay, so that means the mean time for the searcher to find the target is actually infinite. Okay, for pure diffusion. So now the question is, what happens if I just introduce the resetting? So why does it become infinite? I mean, intuitively the physical reason is very clear, because what happens is that the trajectories that contribute to the mean. So there are trajectories which actually wander away to the opposite direction to plus infinity, and they make the mean time divergent. Okay, so what resetting does when you switch on a resetting is to cut off these wandering trajectories and makes it finite. And how do we compute that? It's very, again, sort of easy to compute. I'll not go through the details of the calculation, but again, the idea is to use the same renewal structure. So you want to calculate the survival probability in the presence of resetting, right, R, starting at x naught up to time t. Again, if there is no resetting, which happens with e to the power minus RT, and then you have to just calculate the survival probability without resetting, which we know already. Or else, you look at the last resetting time, tau, and then you see that, from here to t minus tau, you have to, just self-consistently, this should be QR of x naught, whereas from here to here is just Q0, because there is no resetting here. So you can convince yourself that this is an exact equation, and you can actually even solve the backward Fokker-Planck equation also. And so this is like a Swinger-Dyson equation. So you can self-consistently solve it. It has a convolution structure. You can solve it exactly in the Laplace space. But from that, you can actually compute the mean capture time or mean first passage time. And it has a very simple formula. It's 1 over r, exact formula, exponential of square root of r over dx naught minus 1. Okay? So what does it mean? So first of all, for any finite r, the mean capture time is now finite. Recall that r equal to 0, it was infinite. So that means any amount of resetting actually makes it finite. Okay? Which of course as expected, because as I told you, it cuts off the wandering trajectories. But what is interesting is that if you plot it as a function of the resetting rate r, the mean first passage time, you see it diverges at the two ends. When r goes to 0, it diverges, and when r goes to infinity, it diverges, and with a single minimum in between. And why does it diverges at the two ends? Again, when r is 0, just pure diffusion, you have these trajectories which takes it away on the opposite side, so which makes the mean divergent. On the other hand, if your r resetting rate is very large, it's like this Zeno's process. That means you keep resetting the particle exactly at the starting point. So that means you localize the trajectory very strongly to its beginning position, and as a result, it cannot find this target. Okay, so it diverges at both ends with a single minimum in between. So, and this is actually which you can compute of course explicitly in terms of dimensionless units. This is just given by the roots of a transcendental equation. Okay, so what this tells you is that I mean not only resetting makes the process efficient, there is indeed a sort of optimal resetting rate which makes the mean time to find the target minimal. Okay, and so this is the sort of main finding about 10 years back. And then this fact was found to be very robust. That means this fact that there is an optimal resetting rate which makes the search process efficient, and this was found in many different systems. I don't have time to go through all this. It happens for diffusion in all higher dimensions. It happens in many other different types of processes, and also in in the context of active run and tumble dynamics and so on. So we wrote a recent review on this. I mean, but the field is developing so fast that even after this review, which was 2020, there are many papers which came out after that, and in particular the experiments. So as I said, theory is very rapidly developing. So how about experiments? Okay. So there's two recent experiments. So there is one I already mentioned, which was from the group of Yael Roikman at Tel Aviv University, and the other is from Sergio Siliberto's group at ENS Leo. And I'll talk about the second one because I was involved with them. So the setup is very simple. So essentially you have these optical tweezers and you have these silica balls immersed in water, and then you can actually find out the trajectory of the particles. Now you can ask that why do we bother to do experiment? I mean the theory is very simple, you can calculate everything. Why do you want to mimic the experiment? Okay, but the point was the experiment was actually important, because what was not clear to me to us is that how do you actually mimic the the resetting process in real experiments. Okay. And this was actually interesting. So what Sergio came up with this idea of basically, so what you have in your system, you have the free diffusion and then some resetting, right? So how do we mimic this? So the idea was to let the particle diffuse freely for a while, and then you switch on the optical trap and you let the particle relax in the optical trap, and that's and you don't take many measurements during that period. And that's a sort of mimicking the resetting process. Okay, so there are two-step process. So you have free diffusion for a certain period, which can be periodic, deterministic, or random exponential distribution, and then you switch on this optical harmonic trap and you let the particle relax to its equilibrium distribution, and this is the sort of quote-unquote resetting. But the only trouble is that and you alternate these steps 1 and 2. The trouble is that you can relax, but it relaxes to its equilibrium distribution. And in harmonic trap, this is just a Gaussian distribution with a finite width sigma, which means that every time when you reset, you actually don't reset to a particular point like a delta function, but you actually choose the resetting position from a Gaussian distribution with a finite width at finite temperature. Okay. So the question, so this was a question which came up from the experiments, that what does finite width do? Sigma. Okay, what is the effect of finite sigma on this mean first passage time? And then this was very interesting. So what happens is that if you look at the mean first passage time as a function of the resetting rate R, and you have one dimensionless parameter, which is the distance from the target, which is L, and divided by the sigma, width of the equilibrium distribution. Okay, so this is the only dimensionless parameter, and you plot T bar as a function of R, the C is just R, and for different values of B. So B equal to infinity, that means sigma is 0, is a theoretical curve, and there you have this non-monotonic curve with a single minimum. Okay, that was what I showed you before. And now you just increase the sigma, and when you increase the sigma, what you find is that it becomes non-monotonic. It sort of has a minimum, it goes up, and then it goes down to 0 when R goes to infinity, which is actually expected because what happens physically is clear that, I mean, you are resetting and you have a finite width, okay, and your target is somewhere. So just by resetting, if you infinitely reset, you can just find the target just by resetting, okay, without the need to diffusion, okay, if you do infinite resetting. So that's why you actually have another minimum as R goes to infinity. But in some sense, this is a trivial minimum, but the actual minimum stays there. But what was not expected is that there is a critical point, BC, okay, sigma C, below which this becomes monotonically decreasing. So that means there is a spinottal phase transition. Spinottal, that means both the first order and second order derivative disappears when this happens. So below which, when B is bigger than BC, you have this both minimum and maximum, and this is a metastable minimum. But beyond that, it becomes just a single minimum. And this is again a robust phenomenon, this existence of a metastable minimum, and it has been found with other problems also. So I'm more or less done. So let me just conclude and with a summary. So basically what I told you is just a very brief and partial overview of stochastic resetting. It's a very rapidly evolving field of research. So resetting leads to a new non-equilibrium stationary state with a current carrying. It has an unusual temporal relaxation with a second order dynamical phase transition. And in most cases, resetting is a very efficient strategy, and in many cases that there exists an optimal resetting rate, which makes the search process most efficient. And the experiments have led to new interesting questions concerning the effect of finite sigma and so on. And so there are new directions in which we're working now. So one is the geometrical properties of resetting Brownian motion in d bigger than 2. And then, in some cases you have search time which is finite, which means that you have to come back at the end of a fixed time period, and these are called resetting Brownian bridges. So there are interesting new effects there. And then, this has recently been applied to optimal control theory, resetting as a sort of control for the optimal control theory. And then finally, I mean, we are quite actively working now on the sort of the many body resetting problem, both in the classical and quantum setting. Okay, and so the main point is that the stochastic resetting is a very rich and interesting static and dynamical phenomena. And let me end by advertising a recent special issue in JPhys, which they are bringing out a special issue this year, and to commemorate these 10 years of diffusion with stochastic resetting. And there are many interesting articles there with new applications. And finally, let me acknowledge all my students and collaborators, in particular Sergio and his group at ENS Lyon. So that was very interesting to collaborate with them. Thank you very much for your attention.
Some questions?
Yeah.
In the case of the eyes, do we choose
in the case of sorry.
Yeah, in the case of the eyes, do we choose R star?
Yeah, I mean, yeah, I don't know whether naturally people use that. I mean, there have been no actually not systematic study about the visual search. They always just write the pictures. I mean, there's no systematic study. But I'm sure if they do that, probably naturally we choose some optimal value. I mean, it's not been systematically studied. Absolutely, no, absolutely, yes.
You describe a sequential process.
Yes.
Probably with our vision, we do some parallel.
We do some optimization. Yes, exactly. Yes, absolutely. Yes. Yeah. No, I'm sure we choose Alstar.
Is there a way to predict this value of R star depending on the physical model you're considering?
Yeah, I mean, R star is not a universal quantity. It depends on the model and things like that. But the main point is that there is always an R star. Okay, that's the most important point. I mean, the actual value depends on the model and the precise details of the model. Okay. Yes, yeah, you can try to calculate the R star there. I mean, there lots of studies there in the last 10 years. I mean, but this particular thing, I don't know if it has been studied, but certainly the prediction is that there will be always an R star.
Okay, thank you very much.
Thank you.
So the next presentation by Lenka Zdeborova about understanding machine learning with statistics.